let me first tell you guys what the busy beaver function is. So the first notion we need is that of the productivity of a Turing machine. So if you have a Turing machine and you start it on an empty input, and it works, and eventually outputs a sequence of n1s with nothing else on the tape, and stops, then we say that the productivity of that Turing machine is n. And if anything else happens, we'll just say that its productivity is 0. So in particular, a Turing machine that never stops has productivity 0, even if the reason it never stops is it just keeps writing ones forever. And productivity is an interesting notion because it's so much harder to write a large number of ones and then stop than it is to just write infinitely many ones and go on forever. So the busy beaver function is just a measure of productivity. So what it is if you give the busy beaver function an input n, it outputs the productivity of the most productive Turing machine with n states or less. So it's basically how big a finite number you can generate with n states. So what we're going to do is prove that the busy beaver function is not computable. And as you guys will see, that will turn out to be a pretty useful result. So we're going to use the same method we always use. So what we're going to do is we're going to proceed by reductio. So we're going to assume that the busy beaver function is computable, and then use that to build an evil Turing machine, which does something impossible, and conclude that the busy beaver function was not computable after all. So we assume otherwise. In other words, we assume that some Turing machine M busy beaver computes and of course, what it means for this machine to compute the busy beaver function is that if you start this machine with a tape which is blank except for k1s, then it'll output busy beaver of k1s and stop. So what we're going to do, we're going to use the busy beaver machine to build the evil Turing machine, ME. And it is super easy to build. So I'm just going to describe the plan informally first. So the way the evil Turing machine is going to work is we're going to start it out with an empty input. And the first thing it's going to do is write down n1s for some large n. And then it's going to duplicate the size of that sequence. And then it's going to use the busy beaver machine as a subroutine to compute the busy beaver number of that string, the one it just generated. So basically, it's going to compute busy beaver of 2n. And then it's going to add 1, and it's going to stop. Super simple. That's all it does. So print n1s, duplicate string, apply busy beaver, add 1, and stop. Now, something to note here is that n here is fixed. So n is not the input we give it. So this is what it does on an empty input. So in specifying the program, we have to say in advance what number n is going to be exactly. And I have not yet given you enough information to know what it is. So the one thing I've said, and that's going to be crucial, is that n is large. So what I'm going to do is I'm going to go on, and then I'm going to come back to tell you just how big n needs to be. So let's count the states in E. So maybe I'll give letters to, or numbers to these. OK, so for 1, so how many states do we need to print n ones and then bring the reader back to the beginning of our string? There are much better ways to do it. But one way to do it is to just use n plus 1 states. That is like the like kindergarten way of doing it. Because what you do is you just start with a state that says print a 1, go right, and go to the next state. And then the next state says print a 1, go right, go to the next state, and so forth until you get to the nth state, which just says, OK, now start going back. And then the plus 1 just tells you when to stop. So that'll do it. I mean, there are much better ways of doing it. For example, a different way to do it would be to start out by writing the thing in binary notation, and then have a fixed number of states that extends it into the unary notation way. So for small numbers, that's going to require more states. But for big numbers, that's going to require much fewer states. OK, but this is all we need for these purposes. OK. For 2, we need to duplicate the string. So that just requires some number b, which is independent of n. And that's the crucial thing. Doesn't matter how big it is, it just means that it's independent. But in fact, we know that it's quite small. In fact, I think that designing such a Turing machine is a homework exercise. Now, for 3, the number of states we need is exactly the number of states in the Busy Beaver Turing machine, MBB. And again, crucially, this number is independent of n. So it's just constant relative to n. And finally, to add 1, we just need some small number of states, c, which again is independent of n. So here is the number of states in our evil machine. It's just n plus 1 plus b plus that guy plus c. In other words, it's just n plus some constant beta. This means that it's easy to pick n big enough so that the following is true. If you just pick n to be bigger than beta, then that condition is going to hold. And this is the trickiest part of the proof. So the trickiest part of the proof is just to keep track of the fact that n is fixed. It needs to be fixed from the start. But I didn't tell you at the start just how big it was going to be. I only was able to tell you now that we have beta on board. And the reason I did that is that in order to know what beta was, I first had to explain how the machine worked. But if one was doing this, if one had unlimited amounts of time and patience, then the way to do this would be to very carefully see what B is and see what C is. You're, of course, never going to know what that is because it doesn't really exist. But our assumption is that it does exist, so you would be able to calculate it. And that would be enough to know what beta is. And that would be enough to know what n is. And then you just build that into the specification of your machine. OK, now the fun part begins. So now we're going to show that the evil Turing machine is impossible. So the way to see that it's impossible is to see that we get conflicting results when we look at the output of the machine and when we look at the results of our counting exercise. So by looking at the output of the machine, we can conclude this. We know that, and I'll explain it. So remember what the evil machine does. It just works on an empty input and delivers busy beaver of 2n plus 1. That means that the productivity of the evil machine is that. So we know of at least one machine with as many states as the evil machine that has that productivity. So if you now say, OK, what is the result of applying the busy beaver function to that many states? Well, we don't know what it's going to be, but we know that it's at least this. Because remember, the busy beaver function gives us the productivity of the most productive Turing machine with k states or less. So if that turns out to be the most productive Turing machine with that many states, then we're going to have an equality here. If there's another more productive one, then we're going to have an inequality. So we know that. OK, but now let's look at this result from our counting exercise. Because we know that, we know this. Because 2n is at least as big as that, and if you allow for more states, the busy beaver number is never going to go down. It can only go up. So that has got to be true. And then we're done, because these two are inconsistent. What in the universe could be cooler than that? So there can be no such thing as the evil Turing machine. So there can be no such thing as a Turing machine computing the busy beaver function. So the busy beaver function is not computable. So maybe I can do this. Maybe I can write down how many ones will be on the tape after each of these things. So at this point, we'll have, after that, we'll have n strings on the tape. After that, we'll have 2n. After that, we'll have busy beaver of 2n, so an enormous number. And then after that, we'll have that. And then it stops. OK. And then the counting exercise that we did was just try to see how many states we would need to build such a machine. And we came up with an upper bound, which is like not particularly elegant, but it's enough for these purposes. So to do the first thing, all you need is n plus 1 states. I mean, that's more than enough. To the second thing, I forget how many we need, but it's going to be some small constant. And then for 3, well, we have no idea what that number is, but on our assumption, that number exists. And again, it's constant. It does not depend on how big n is going to be. And then finally, C is just add 1, again, some small number of states. Yes?
For the evil machine, are you just, is the add 1 step just to create this, so it could be anything? There's no reason you pick, OK.
Yeah, it's totally ad hoc so that we can get this reasoning to work. And the proof is pretty robust. I mean, like, I picked one way of doing it, but like there are many ways of implementing tricks of this kind. So what we need is we need there to be a mismatch between what we know about the productivity of these machines just by counting and what we know about its productivity by looking at the kinds of outputs it generates.
I guess what I would use that is if you just didn't add the 1, then you wouldn't have the inequality.
So because there was no microphone, I'm just going to repeat your question. So if you didn't add the 1, then you wouldn't have an inequality. That's right. No, that's right. So for this version of things, you absolutely need the 1. But what I'm saying is that it doesn't have to be this particular sequence of operations. It's just that's just one way of generating this kind of mismatch. But you're absolutely right in your first point. So for this recipe, we do need the 1, and the reason we need it is just to get these results. Oh yes. So 1, 2.
I have multiple questions. First of all, I'm still a little confused how you got n+1 states when you're counting states with that first thing when it's n+1 states. How'd you get that?
Oh, right. It could be that I made a mistake. So let me.
No. I'm sure you didn't make a mistake. I just don't understand. Like, you've said it a couple times. I just don't get it still.
So let me repeat the method that I had in mind. So you first have n different states that do the following. The first state says print a 1, move to the right, and go to state 2. State 2 says print a 1, move to the right, and go to state 3, and so forth. So state n-1 says print a 1, go to the right, and go to state n. And then here you are. You're in state n, and all you need to do is add 1 more 1, and then go back. So state n says print a 1, go left, and enter state n-1.
Okay,
Sorry, n+1.
That makes sense. Here's my next question. How do you guarantee that this beta is less than n? I know you said for big enough n, but like it's kind of weird to me. Like
Yes, that is the weirdest aspect of the proof. That is the weirdest aspect of the proof. So it feels a little bit circular.
Yeah.
So this would be the way to do it non-circularly. So let's suppose with the assumptions of the proof that there really is the busy beaver machine. So it's there, and it has a certain number of states. So just take that number, and I'm going to call it, say, m. And then
sorry to interrupt, but it actually wasn't that I was too worried about. It was actually more B and C. Like.
Oh, right. OK. So then.
I understand that like that's whatever, and we don't really know. But
that's right. So B and C. So B is just the number of states of some machine that whatever input you give it, it duplicates it and goes back to the beginning. When you do your homework. In fact, I think that this is what it did for the homework. I think what the homework does is it asks you to calculate B and C.
Oh.
So it asks you to generate Turing machines that do exactly those things. And then I can't remember how I did it, but it's probably then something like, OK, then count them all. What number do you get?
Oh, I see. OK. Yeah, I haven't done the homework yet.
OK, but then the idea is, so you actually like produce your Turing machine. You see how many states you needed. You produce your Turing machine that just adds 1. You see how many states you needed. And then you just add 1 plus b plus m plus c. And you could just let n be that. So then you go back to the beginning, and you say print n once. And by n, you mean like the thing you really calculated. And then it's going to turn out that you're actually going to be able to prove this outright. In fact, in this case, it's going to be an inequality without having to specify for big enough n, because you will have used the right n from the start. I'm very glad you asked that, because that is a tricky thing.
I understand that. Thank you.
OK.
So 2 questions. The first question being, if number 1 is allowed to depend on n, why isn't number 3 allowed to depend on n? Like, could we just say busy beaver depends on n?
Right. It's to do with how we're thinking of the busy beaver function. So the evil machine is a machine that just starts on an empty input. So its ability to start out by printing n once is going to have to be like hardwired into the program. But the busy beaver machine works very differently. So the busy beaver machine takes an input and then works on the base of that input. You know, the busy beaver machine on its own doesn't have to know about n. You know, it just works with whatever you give it.
Then the other question being, when we're constructing really weird proofs to try and like determine that this machine or that machine is wrong, how can we make sure that like the busy beaver machine is at fault and not the larger construction?
Nice. That is always a problem. So, in fact, this will be a preview of one of the reasons the Gödel's theorem is so exciting. So we grow up thinking that once you prove something in math, like you're sure forever after what went wrong. But in fact, that's not the case. So in fact, when you prove something, you can only trust the results if you know that your setup is consistent. And a consequence of Gödel's theorem is that it's very hard to be sure that your setup is consistent. That holds in general, and it definitely holds for this case. So what happened is that I made a bunch of assumptions about, like, you know, what's allowed and what's not. And then I said, OK, and now make this one further assumption that the busy beaver machine exists. Provided the rest of the setup is consistent, if we reach a problem, then what has to be at fault is that additional assumption. But I think you're absolutely right, that that's only modulo the idea that the rest of the setup was indeed consistent. And you know, it's you know, if someone said, like, would you be willing to have someone like chop off your arm if the rest of the setup is not consistent? I would say no. Like, you know, I'm pretty sure, but like I'm sure enough for this class, but like not sure enough to bet my arm on whether that's the case. And I think that's true in general for mathematics. OK. So the rest of the class, I just want to do something fun, which is, in fact, was inspired by Scott Aronson. So as I mentioned last time, when he was very young, published a paper suggesting a big number competition. So the idea is you have 2 people, and they take turns, and one person names a number. It has to be a finite number. And the next person names a bigger one, and a bigger one, and a bigger one, and whoever names the biggest number wins. Now, there's certain assumptions that need to be made for this not to be boring. So, for example, one way for it to be boring would be for just, you know, you name a number, and I say, well, that number plus 1. And the other person says, well, that number plus 1. And then it just becomes a war of patience rather than a war of mathematical creativity. So, so I think one needs an agreement between participants, according to which the next entry in a competition has to be not just bigger, but much bigger. And what that means is that it has to be so big that you can't reach it in practice using only tools that have already been introduced in the competition. So if you know, you were writing a really big number using exponentiation, then my number has to be so big that, like, even if I start you know, just writing these like enormous strings of exponents, like you know, people would get bored and leave before I managed to reach your number. Of course, every number is reachable in principle using like any technique. It's just that you know, what I'm talking about is reachable in principle, like in the setting of the competition. Okay, so that's the first rule. Now, another way in which the competition could get boring is if semantic vocabulary is allowed. So if we're allowed to talk about what various names refer to or what's true and so forth, because then I can say the following. I can say, OK, my only entry ever is going to be the biggest number you will ever name plus 1. So, that's, that's not interesting. And of course, things could get worse if both people say that at the same time. So no semantic vocabulary. So you need to just write down the name of a number on the board. Now, one thing that is allowed is to make up notation. So as long as you explain to the audience what your weird U notation means, then that's a valid entry. Okay, so that's the competition. A few years ago, I have this friend he's a philosophy professor at Princeton. His name is Adam Elga. And at some point, he called me on the phone and he said, we should do this competition. So we actually did it. He came to MIT and we booked a big classroom and we did it. And I want to tell you about his first move because it was genius. Okay, so I went first. And I had read Scott Aarons' article in which he points out that much better than just writing 99999, it's to write just a bunch of ones because you can write them faster. Okay, so my first entry was something like that. And then Adam looked at it and he obviously had a moment of clarity and he just got the eraser and went like this. $11 factorial, 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 factorial. That is actually that's that's a biggish number. It did take a little bit to go beyond that. Okay, so let's play the game. Let's do the competition. So suppose that you're in my position after this move. So what do you do next? What's your next entry to this competition? And remember, it has to be much bigger.
Just take the busy beaver function of that number.
Beautiful. Beautiful. OK, so that is the way to go. There's no question about that. Let's talk about it. Before then, let me just say something about how we did it clumsily in practice. So before getting to truly big numbers, which are those, we attempted to do things like say, well, look, if you take n factorial, that's smaller, but of the order of n to the n. So if you start iterating, so if you use that construction, that's kind of like saying 11 to the 11. And then that, and then do this again. And then so forth. So I forget exactly how it worked, but at some point, one of us just introduced this new notation where, let me just call it alpha. So then alpha of n is just the result of iterating this construction n times. And then one could just say, OK, my next entry is going to be alpha applied to a Google. OK, that's much bigger than this. So now let's get real. So now let's talk about how to generate big numbers. So it's true. If you're to be a worthy competitor in this sort of competition, you need something like the busy beaver function. So can anyone say why any of these tricks would be blown out of the water by, say, that? So why is this number much bigger than this one? Yes?
Because the alpha operation is fully doable within a Turing machine in much less than a Google operation.
Exactly. A Google States. Exactly. That's exactly right. So I mean, forget about Turing machines. Say that you're using BASIC or C++ or something, and someone says, like, I'm going to give you like a Google state, or I don't know, Google lines of code. Can you program a computer that, like, given enough time, writes out that number and stops? Of course you can. Like, you can do it in, I don't know, under 100 lines. So this number really, 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 really is much bigger. Like, really. OK, so you're in the competition, and your opponent has just written down this. What's your next move? Yes.
You could go nesting busy beaver a number of times.
How about that? OK, yeah, that's bigger. That's definitely bigger. OK, so what's next? This, by the way, was one of the smaller entries in the competition. OK, so I'm going to give you guys a cool hint. So notice the following. Notice that if someone were to give you a black box, you have no idea how it works, but it computes the halting function for you, then you can use that to build a machine that computes the busy beaver function. So remember, the halting function is just a function that tells you whether a given Turing machine halts. So you give it the number of a Turing machine, and it says yes or no, depending on whether it halts, 1 or 0. So can anyone tell me how to use that box to build a machine that computes the busy beaver function?
So I'm just going to assume you have some sort of the numbering you're using for Turing machines gives you some nice sequential order in increasing size for convenience. And then with that numbering, you just go through all the Turing machines up to through whatever size you're checking. And then for every Turing machine, you first run it through the halt through our black box. If it doesn't halt, we ignore it and move on. If it does halt, we emulate that Turing machine, get its output, and just store the largest output we've gotten so far. Once we've gone through every Turing machine, we'll have the largest output that we can get.
That's exactly right. So the whole problem for these things is that you don't know whether machines are going to halt, because we know that we can simulate machines. So it's in principle possible to say, well, just go one by one. But of course, if you get trapped into one that never halts, then your procedure is never going to terminate. But if, as you suggested, you first use your magic box to check and see whether they're going to halt, then this procedure is well defined. It's always going to terminate, and you could calculate the busy beaver function. So people sometimes refer to these magic boxes as oracles. So you have the notion of a Turing machine, and then you have the notion of like a Turing machine plus a super Turing machine, which is a Turing machine equipped with a halting oracle. So hint, blow that number out of the water by using the notion of a super Turing machine.
We can first note that for a super Turing machine, since its instructions are a strict superset of the Turing machine's instructions, its busy beaver function is going to be, like, if you do busy beaver but with the super machine, that's going to be strictly larger. but we can actually go even further and note that the supermachine, if we look at supermachine instructions, we can do a pretty similar construction and find it has basically the same halting problem. So we can make a super Turing machine, and we could do, some very large number of supers Turing machine, use its equivalent to the busy beaver function, do that a large number of times, and get something a lot bigger.
Good. So what you just did was do the two next steps of our competition. So what happened in our competition is that the next step corresponded to the first thing you said. So the next step is to do this. The next step is you say let BB sub 1 be the busy beaver function for super Turing machines. So in other words, the busy beaver sub 1 of k is the productivity of the most productive super Turing machine of k states or less. And the reason this number blows all of that out of the water is that you can use far fewer than that many states to define the regular busy beaver function in a super Turing machine. So little constructions like this one, where you just say, apply the busy beaver function a Google many times, are super easy to produce in that states or less. So if you now take the most productive super Turing machine with that many states, it's going to blow everything we had out of the water. OK, so that was the first component. And then the second component is, why stop there? So it's indeed true that the halting problem for super Turing machines is not super Turing computable, and that the busy beaver function for super Turing machines is not super Turing computable. So we can just iterate this procedure and define that and that. And each of those are going to get bigger. And each time you'll have done something much bigger. So how about if we have the next entry in the competition just be this? OK, so that's the next entry. What do you do next? And a hint here is, remember that we have already discussed infinite ordinals. Now, the entries in the competition have to name finite numbers. But that doesn't mean that we can't use infinite numbers in characterizing the finite numbers. OK, so we're sort of running out of time. So I'm just going to tell you guys. But this is the funnest part. So there is no reason why this sequence needs to be restricted to the finite. So it's very easy to define what that means. So that's a busy beaver machine equipped with an oracle, which is capable of deciding halting problems for oracled Turing machines of all finite levels. So if you're a Turing program equipped with an oracle of type k, then for any finite k, Turing machines of level omega can decide that issue. And the busy beaver function level omega calculates productivity for those Turing machines. And you can keep going. So after that, omega plus 1, and then omega plus omega, and omega times omega. And it turns out that the real limitation is this. When you have a Turing machine with an oracle, you need to be able to pose the problem to the oracle. So you need to be able to say something like, does the nth Turing machine with oracles of type blah halt? And when blah is an infinite number, you need some way of describing it. So the real limit to this procedure is countable infinite ordinals, which are such that they can be finitely named. And the ones that can be finitely named, well, at least a nice big class of them, are the ones that can be described by Turing machines. So those are the countable ordinals that are called recursive ordinals, because those are the ones such that there is a Turing machine that tells you, that describes the ordering. So if you give it two numbers, it tells you, according to that weird ordering, which one goes first. So you can carry out this procedure all the way up to the first non-recursive ordinal. So homework question, if you guys want. Your opponent has just written that down on the board. What's next?